Yeah, so this is the problem set. We has 5 problems. They're all typical um, heat integration problems. And I'll just start solving them now. And if you have any questions, just jump in, shout, and let me know. And again, your exam will basically have 3 questions, 3 of these types of problems. There's no multiple choice, nothing. And you'll have to work through it. You'll have to develop the heat exchanger network and just upload your work, okay? And when it comes to these types of problems, there really isn't um, a lot of space for creativity. It's all about following the procedure and just trying to develop your develop the networks, okay? So I'm going to start off by solving the first problem here. And so given the following process streams and a delta T minimum of 10 degrees Celsius, build the interval table, build the cascade diagram, and determine the pinch point, minimum heating utility, minimum cooling utility, and then finally develop a heat exchange network to achieve maximum energy recovery. Okay, so let's start just going through the steps. Let me share the whiteboard. Right. Let me move this guy to the screen. And your first step will always be to just write the information you have, or one second. So hopefully everyone can see my screen. If you can't see it for some reason, just let me know. And okay, let's start. So we're doing problem number 1 here. Let's get out of the way. So this is 4:30, October 26, problem 1. Okay, so first step, I'm gonna just write the stream information I have. So again, just stream number, your source temperature, right? Your target temperature, and your heat capacity flow rate, which is CP. And this is usually in units of energy per temperature. So Kelvin and Celsius are interchangeable in terms of deltas. So having megawatts per Kelvin, when you multiply it by delta T in Celsius, it's fine. Okay, so just be aware of this point. We talked about it last week, that even though this is megawatt per Kelvin, you need to understand that delta in degrees Celsius is equal to delta in Kelvin, right? This is valid for these two degree measurements. It's not necessarily valid for Celsius Rankine, Celsius Fahrenheit, Kelvin Fahrenheit. These relationships are not valid. Rankine Fahrenheit, I think it's valid because it's also a similar, just straight addition, okay? Okay, so let's write our streams. So in this case, I have 3 hot and 2 cold. So I'm just gonna, this is the notation I use, H1 source temperature or supply temperature goes from 200 to 100 and has a heat capacity flow rate of 0.4. H2 goes from 200 to 100 and it has a heat capacity flow rate of 0.2. I'm just copying what's written on the table. H3 starts, the third hot stream starts at 150, has to be cooled down to 60, and the heat capacity flow rate is 1.2. Then I have my first cool stream, C1. I have to heat it from 50 to 140, heat capacity flow rate of 1.1. And C2, I have to heat it from 80 to 120 and a heat capacity flow rate of 2.4. Okay, so this information is just a given. I didn't do anything. So step one will be always step number one. I need to subtract delta T minimum from hot streams. This is very important. This is the first step in this process. And in this problem, you were given the delta T minimum was 10 degrees Celsius. So this is the second piece of information you should, or this is the piece of information you should always note at the start of the problem, okay? A very common error is that if I give you two problems, first one delta T minimum 10, second problem delta T minimum 15, just use 10 when solving all the problems. No, just double check the value you're given for delta T minimum before doing anything, okay? Just make sure you're using the correct value. So I'm going to subtract 10 degrees Celsius from all my hot temperatures. And my hot temperatures does not mean the higher temperatures. It just means the temperatures, all the temperatures in my hot streams, right? So if this is, this is a dividing line, I'm going to subtract 10 from these temperatures only. I'm not touching these guys, okay? So 200 minus 10, this will be 190, 100 minus 10. This is 90, 200 minus 10, 190 again. This is 90, 150 minus 10 is 140, 60 minus 10 is 50, okay? So this is the first step in the process. I subtracted delta T minimum from my hot temperatures. Okay, so after doing step one, I'm going to move on to step two. And step two means, step two will involve me identifying my intervals, arranging my streams along these intervals to identify, which stream crosses which interval really. So this now step number two will be arrange temperatures from highest to lowest and identify your intervals. And this is up to you, whichever way you want to do it. However, the easiest way I find is to first of all just list the temperatures from highest to lowest. So what's my highest temperature here? It's 190. What's my second highest temperature? So I have 140. My third highest temperature will be 120, right? 190, 140, 120. 190, 140, 120, right? My fourth highest is 90. Then I have an 80 and a 50, right? 80 and 50. So here I'm arranging temperatures from highest to lowest. Always double check this list because it's not that obvious, to just arrange a list of numbers, right? Especially if you're not using a computer, it's very easy to drop a number here. And if you drop a number and you have an interval missing, your calculations will be you're gonna get very strange numbers. And they're not gonna match your network, and it's just make it hard to fix the problem later. Okay, anyway, so I arrange my temperatures. Graphically, the easiest way to plot the streams and identify the intervals is to just draw a horizontal line next to each temperature, right? So I just drew a bunch of horizontal lines. And once you get to this point, I'm going to do two things. First thing, I'm gonna identify my intervals. So this is my first interval here, right? This is my second interval, third interval, 4, 5. So in this problem, I have 5 intervals. An interval is basically the gap between two adjacent temperatures after I arrange them. And now I'm gonna plot my streams. So let's plot them. So I have H1 here. It goes from 190 to 90. So it just goes from 190 all the way to 90. H2, this guy goes from 190 to 90 as well. H3 from 140 to 50. from 140 all the way to 50. I have C1, which goes so we said C1, it goes from 50 to 140. So just 140 all the way to 50. And again, just draw these straight lines. C2 from 80 to 120. C2 goes from 80 to 120. Okay, so now I identified the intervals. I plotted or drew my streams over these intervals. So now what's the next step? The next step will be to build the interval table. Okay, so let me save this screen, and then let's write. So step 3 now will be to build the interval table. I'm going to do it on this side here. And again, if you're having any difficulty, something is not clear, please just shout it, ask the question. Now is a good time. Okay, so now step 3, build the interval table, right? So the interval table will have 5 main columns, right? The first column will be, I'm just going to put it here, will be interval number, right? Second column will be the initial temperature of each interval. Third column will be the delta T of the interval. Fourth column will be summation of Cp hot minus summation of Cp cooled within that interval. And my final column here will be the delta H within the interval, right? And just recall delta H will be delta T multiplied summation of Cp hot minus summation of Cp cooled. Okay, now I'm going to populate this table. Okay, so let's start with interval number 1, which is this guy right here, the space between 190 and 40. The initial temperature of this interval is 190. So I'm starting at 190 for this interval. 190. The delta T for this interval is now 90 minus 140. This is 50. And then summation of Cp hot minus summation of Cp cooled. I only have 2 hot streams here. And this means basically I'm just adding all the hot CPs and subtracting all the cold CPs. Okay, don't confuse the signs here. Right, so here I have 2 hot streams, so I'm just adding their heat capacity flow rates. H1 has a CP of 0.4, H2 has a CP of 0.2, so summation of these two guys is 0.6, right? And then delta H, which is 0.6 multiplied by 50, will be, this is 30, 0.6 multiplied by 50 is 30. Okay, let's move on to a second interval, interval 2. Initial temperature in this case is 140. Final, or delta T, 140 minus 120 is 20. Summation of Cp hot minus summation of Cp cooled. I have H1, H2, H3, so I have 3 hot streams, so it will be 0.4 plus 0.2 plus 1.2 is what? 0.4 plus 0.2 plus 1.2. This is 1.8, right? Minus C1, which is 1 cold stream here, minus 1.1, and this will be 0.7, right? So this value right here is 0.7, and then delta H 0.7 multiplied by 20, this is 40. Okay. Let's go to the third interval, which is, I'm looking in this block right here now. Delta T, or T initial, sorry, is 120. Delta T of this interval 120 minus 90 is 30, right? Then I have summation of Cp hot minus summation of Cp cooled. I'm going to add all the hot streams and subtract all the cold streams, right? They're all present in this interval. So I'm just adding 0.4 plus 0.2 plus 1.2 minus 1.1 minus 2.4. So 0.4 plus 0.2 plus 1.2 minus 1.1 minus 2.4. This will be minus 1.7. And then delta H will be minus 1.7 multiplied by 30. And this is minus 51. Okay. Let's go to interval number 4 now. The initial temperature in this interval is 90. The delta T in this interval is 10. And summation of Cp hot minus Cp cold, I have H3 minus C1 minus C2. So it's 1.2 minus 1.1 minus 2, 2.4, 1.2 minus 1.1 minus 2.4. This is minus 2.3. And if I multiply this guy by this guy, minus 2.3 multiplied by 10, this is minus 23. And then finally, the final interval here, interval 5, initial temperature is 80. Delta T of this interval is 30, right? 80 minus 50 is 30. Summation of Cp hot minus Cp cold is H3 minus C1. So it's 1.2 minus 1.1. This is 0.1. And delta H 0.1 multiplied by 3. 30, sorry, this is 3. Okay, so I have 30, 10, 30, 20. Good. So now I have my interval table, and this table really has all the information you need to build your cascade diagram, right? So now the next step will be to build a cascade diagram. And I'm gonna do this on the left-hand side here, so let me erase these guys. And it's very important to be organized, you know, make sure you have enough paper. You know, just try to space out your work, give yourself space so that you can catch out any errors and you can troubleshoot your calculations easily, you know. In case you make a mistake, it's common, I mean, to make errors, simple errors here and there. And if you do that, you just make it easy for yourself to step back and be able to troubleshoot it. Anyways, step 4. Build the cascade diagram, right? And the starting point in building the cascade diagram is just draw a number of boxes equivalent to the number of intervals. So in this case, I have 5 intervals. I'm going to draw 5 boxes, right? 2, 3, 4, 5. I'm just going to connect them with some arrows. Okay, now I'm just going to translate the information I have on my interval table onto the cascade diagram here. So let's do this. So here I have my first interval. The initial temperature is 190. The delta H in this interval is 30. Here I have my initial temperature, 140. Delta H is 14. The initial temperature of this interval is 120. Delta H in this interval is minus 51. The initial temperature of this interval is 90. Delta H is minus 23. And this is my 5th interval. The initial temperature is 80. And delta H here is 3, right? 30, 14, minus 51, minus 23, 3. Okay, and then I'm gonna, after building the cascade diagram, step number 5 now will be to add your heats along the cascade diagrams, right? Determine the Qs. So step 5, add heats, or basically determine the Qs along the cascade diagram. Okay, so the way to do this, you start with QH at the top, is equal to 0. Q1 is equal to 0 plus 30. So Q1 is 30. Q2 is 30 plus 14 is what, 44? 44. Q3, 44 minus 51 is minus 7. Q4 here, minus 7 minus 23. This is minus 30. And at the bottom, you call it QC. You can call it Q5, it doesn't matter. QC is minus 30 plus 3. This is minus 27. Okay, so now I have my cascade diagram. I have all my heats along the cascade diagram. So what do I do once I get to this point? Okay, let me erase this. I don't need this anymore. I might need it to, if we made a calculation error, might have to go back. Okay, anyways. So once you get to this point, the next step will be, let's call this step 6, right? You need to locate the lowest heat along the cascade. So where is the lowest heat along this guy? 0, 30, 44, minus 7, minus 30. This is minus 27, right? So this is my lowest point. This is my lowest heat. So it's actually at this point right here. Okay, and this will be my pinch point, right? This will be the pinch point of my network. So this once I get to this point, I can recognize my pinch point. So this will be my, write it here, pinch point, and my temperature at this interval is my pinch temperature, or is my cold pinch. So TC pinch is equal to 80, and then the hot pinch will be this plus delta T. So our delta T was 10, will be 90, right? 80 plus 10, or 80 plus delta T minimum. Delta T minimum, right? Not delta T of the interval. Delta T minimum will be 90. Just rewrite this here. So TC, or just a TC pinch plus delta T minimum is equal to TH pinch, right? This is how you get your pinch points. So once I get here, what's the next step? I need to, so now, you know, all these steps are along the cascade diagram, right? Step 7, add heat so that the pinch point, so that, let's rewrite this, so that Q at the pinch point is equal to 0. So that Q at pinch is equal to 0. So how much heat do I need to add here for this to be 0? I need to add 30. So I'm going to add 30. So this will be plus 30, plus 30, 60, plus 30, 74, plus 30, 23, plus 30, 0, and plus 30, this will be equal to 3. So I added enough heat so that my Q at the pinch is equal to 0. Okay, this is very important. And once you get to this point, now you identify the two main parameters, you know, or, you know, summarize maybe, you know, let's call this step 7.1. Summarize your minimum energy requirements. So in this case, I'm looking at the top Q, the bottom Q, and my pinch point. So in this case will be QH is 30, QC is 3, and are they megawatts or kilowatts? So they're in megawatts, right? So 30 megawatts, QC is 3 megawatts, and my TC pinch is 80 degrees Celsius. And what these numbers represent, so this is the minimum heating requirement for these bunch of streams, right? So after I integrate all the heat or transfer all the possible heat between them, this is the amount of heat I need to add to this process to fulfill my energy requirements. And this is on the opposite end, this QC, which is the minimum cooling requirements. So after I, integrate and mix and match all these streams to transfer as much heat as possible, this will be the cooling requirement to fulfill the remaining cooling needs, okay? And it's minimum because, this is the optimum, right? You can always pump in more heat and have a suboptimal network design. But if you want to minimize your utilities, you need to pump in just enough heat or, add just enough cooling so that you're not, increasing your plant cost or over designing or, trying to go uphill against the thermodynamics and just spending money. Okay, anyway, so once we identify these targets, this is what we're going to carry to the next step, which is designing the heat exchange network. So the first half of the problem, you really need to get these three numbers. This is extremely important. Once you have these three numbers, you're happy with them, now's the time to move on to the next step. So let me save this, and now let's move on to the next step. So I'm going to clear everything now.
Dr. Basha, while you clear that, can you hear me?
Yes, I hear you.
How long are we gonna have to do the test? Is it like an hour or the whole term?
You'll have 2.5 hours.
Okay. Thank you.
Yeah, yeah, 3 problems sounds like a lot in 2.5 hours, but you'll be fine. One of them will be cute problem, easy. Anyways, let me clear all of these drawing, clear all of this stuff, and but yeah, just follow the steps and practice. Don't over practice. If you just the night of the exam, if you solve 20 of these problems on the exam day, you're gonna get burned out. Okay, just take it easy. Practice a few of them. Just make sure you understand the steps. Make sure you don't do any calculation errors. Try to be effective when using the calculator. All of this stuff. Okay, let's clear all of these problems. Let's move on to the second part. And the second part will be to build the heat exchange network. Okay, so I'm still in problem 1. So at this point, I have my QC was 30 megawatts, or sorry, QH. My QC was 3 megawatts, and my cold pinch was 80 degrees Celsius. And now I'm going to design my heat exchange network. And again, this is a graphical process, and the first step of this graphical process involves just drawing the streams. Okay, so I'm going to draw the streams. So just start H1 here. So starting temp, and here I'm using the original temperatures, not the temperatures after subtracting delta T minimum. Just use the temperatures in the given problem, in the original problem. So 200 all the way to 100, this is H1. H2 will be 200 to 100. H3 is 150 to 60. C1 will be from 50 to 140, and C2 will be from 80 to 120. Okay, so now I just drew my streams. Next step will be to draw 2 vertical lines, right? Yeah, let's draw 2 vertical lines, or 1 vertical line, whichever you're comfortable with. Basically, I'm just splitting this problem into 2 parts, right? And I'm gonna write the pinch temperatures along this line. So for my hot stream, so this is the cold pinch, it's 80. And if you recall, the hot pinch we said was 90 degrees Celsius. So for the hot streams, I'm gonna write my hot pinch temperature. So it's gonna be 90, 90, 90. And then for my cold streams, I'm gonna write my cold pinch temperature, which is 80, 80, 80, 80. Okay, so I have my pinch point here. I divided my problem into above the pinch, below the pinch, just two parts. And let's, after getting to this point, you need to just have a second look at this diagram and just clean it. So let's look at H1 goes from 200 to 90, 90 to 100. Does this make sense? So it's going down and then going up again. It doesn't make sense really. So H1 only exists above the pinch, right? So H1, so because the lowest temperature for H1 is higher than the pinch, so H1 will only get to 100 right here. Let's have a look at H2, 200 to 90, 90 to 100. So it's going down and then going up. Temperature doesn't make sense as well. So I'm gonna just redraw this line above the pinch. $200, $200. So H2, H1, H2 only exist above the pitch. That's fine. Let's have a look at H3, 150 to 90, 90 to 60. So it's decreasing and then decreasing again. That's fine. C1 goes from 50 to 80, increasing 80 to 140. That's fine as well. C2 goes from 80 to 80, 80 to 120, 80 to 80. There is no delta T here, right? So there's no heat exchange here. So C2 will only exist above the pinch as well. So here I'm just going to draw C2 from here to here. Okay, so now I have my streams. I identified my problem to above the pinch and below the pinch. So now let's start matching. But before matching, it's always good to, I recommend you guys do this, is just put some details on the side here, so which will help you matching, which will help you when matching these streams, okay? And the details you need to put will be the, let me use a different color. Will be the delta H and the CP, right? For each stream above and below the pinch, right? Delta H and CP. The CP, you just copy it. So CP here was 0.4 and there is no H1 above the pinch. For H2, it's 0.2, doesn't exist, sorry, below the pinch. For H3, the CP was 1.2 and the delta H is 90 minus 60, which is 30, multiplied by 1.2. This is 36, right? So this is basically the amount of heat available in the stream below the pinch. For C1, the CP is 1.1, is given, and the delta H will be 80 minus 50 multiplied by 1.1. So again, sorry, 30 multiplied by 1.1. This is 33, and this represents the amount of heat required, or amount of heat needed by C1 below the pinch. And for C2, the CP is 2.4 and it does not exist below the pinch. Okay, let's do this on the other side as well. So again, the CPs will be the same. Let's just write them 0.4, 0.2. These are just given in the original problem statement. 1.2, 1.1, and 2.4. Okay, delta H, 200 minus 100. 200 minus 100 is 100 multiplied by 0.4. This is 40. So this stream has 40 megawatts to give. 200 minus 100 multiplied by 0.2 is 20. This stream has 20. 150 minus 90 is 60. Multiplied by 1.2 is 72. So this stream has 72 megawatts. C1, 140 minus 80 is 60 as well. Multiplied by 1.1, this is 66. So C1 needs 66 megawatts. And let's have a look at C2, 120 minus 80. This is 40. And 40 multiplied by 2.4, this is 96 megawatts. So C2 has 96 megawatts, which needs. If you're not clear on how I got these numbers or how I got this diagram, please let me know now. Or, if you're watching the recording, come to office hours, because this is really the key to building your network, okay? And now we're gonna start solving each problem separately, above the pinch and below the pinch. And the rules of the game here, which you need to remember, is above the pinch for matching, CP hot has to be less than or equal to CP cooled. Okay, this is the first rule. You have to remember this, and there is absolutely no cooling above the pinch, right? No cooling. You should never cool these hot streams above the pinch. Please remember this and when solving the problems. Okay, this is extremely important. Okay, now let's go below the pinch. Let's just write the rules before doing anything. Below the pinch, it's the opposite. CP hot has to be greater than CP cooled, and below the pinch, there is absolutely no heating. Okay, no heating. So below the pinch, you should never touch the cold streams with a heater, with a heater, right? And above the pinch, you should never add a cooler on the hot streams. This is very important to remember. Okay, so once we get, let's approach each side alone and let's do the matching, do our calculations, see where we can get with this. Okay, so let's start with H1, and again, CP hot has to be less than CP cooled. H1 has a CP of 0.4, and I'm matching it with the first cool streams. And again, you're matching hot to cold. You're never matching hot to hot. You're never matching hot to hot, okay? Except in certain cases where you have, maybe supercritical fluids, or, if you have a hot stream, which is, 1,200, extremely hot, then yeah, you can consider it higher. But for the sake of problems we're doing, sake of your exam, should never match hot to hot. You're always matching hot to cold, okay? Okay, so let's start with H1 has a CP of 0.4. I'm looking at the first cold stream, which is C1, has a CP of 1.1. So I'm comparing 0.4 to 1.1. CP hot less than CP cold, yes, 0.4 is less than 1.1. So I can connect these two streams and transfer heat between them. So let's have a look. H1 has 40, C1 needs 66. Okay, so I'm just going to, let's start from this end here. I'm going to connect this heat exchanger between H1 and C1. I'm going to transfer 40 megawatts. And this way I satisfy the H1 requirement. So H1 is done. It had 40 megawatts of excess heat. They're all been used, so I don't need to do anything else. Okay, let's go to H2. So H2 has a CP of 0.2. So actually before moving to H2, let's calculate how much energy is left in C1, just to keep track of what we're doing. So C1, I gave it 40 megawatts from H1. It needs 66, so how much is left? 66 minus 40 is 26. And doing this will help you make decisions in a more systematic way instead of haphazardly matching the streams. Because, there's a tendency to match H1 to C1, H2 to C2. But, if you know exactly how much heat is left, you can do this in a better way, or, in a more organized way. Anyways, let's have a look at H2. CP for H2 is 0.2. The CP for C1 is 1.1. So 0.2 is less than 1.1. So I can connect these two guys. So I'm going to connect the heat exchanger from H2 all the way to C1. H2 has 20 megawatts. C1 needs 26 megawatts. So I'm going to transfer 20 megawatts from H2 to C1, and this stream is done. Okay, and now I transferred 20, so there's only 6 megawatts left in C1, which I need to find somewhere. Now let's have a look at H3. So H3 has a CP of 1.2. C1 has a CP of 1.1. Can I make this connection? No, I can't, because this is higher than this. 1.2 is higher than 1.1. So let's move on to C2. H3 has a CP of 1.2. C2 has a CP of 2.4. So can I do this match? 1.2 is less than 2.4, so this match is valid. So I'm going to connect the heat exchanger from here, from H3 to C2. And H3 has 72 megawatts, C2 needs 96. So I'm going to transfer all of the heat from H3 to C2, 72 megawatts here. So H3 is done. So I fulfilled all my hot streams above the pinch. And how much energy is needed by C2? So 96, I gave it 72, 96 minus 72. This is 24. So my two cold streams here still need 6 megawatts and 24 megawatts. And there's no energy left in the hot stream. So I'm going to add a heater. So this will be QH worth of 6 megawatts. And this will be a QH with 30 megawatts, okay? And to verify your calculations, you need to look at the heating QHs here. So if I have a look at summation of my QH, 6 plus 30, sorry, 6 plus 24, this guy is 24. Yeah, because C2 needs 24 megawatts, so I'm giving it 24 megawatts to just fulfill these requirements. And my summation of QH is 6 plus 24, 30 megawatts. And this number has to match the number you get from your cascade diagram. If they match, it means your calculations are algebraically valid. Okay, now let's move on below the pinch. And below the pinch, the matching is CP hot has to be greater than CP cool. I only have two streams, H3 and C1. Let's look at the CPs. 1.2 versus 1.1. CP hot is greater than CP cool, so I can connect these two guys. So I'm going to connect them with a heat exchanger. And how much heat am I transferring? H3 has 36 megawatts. C1 only needs 33 megawatts. So I'm just going to transfer 33 megawatts from H3 to C1. This way C1 is done. And then I have H3 will have how much? 36 minus 33 will have 3 megawatts left, which I need to get rid of. So I'm going to add a cooler because there's no other avenue to dissipate this heat. So it'll be QC, 3 megawatts. And again, your QC or summation of QC should match the number you get from your cascade diagram, which is the case here. So this means that my algebraic system is valid, okay? And once you get to this point, all your streams are completed above and below the pinch, then this is your optimum heat exchange network for this, for these bunch of streams, okay? And this will be the end of the problem, basically, right? So again, steps, start with your table, subtract delta T minimum, then identify your intervals, build your interval table, translate your interval table onto a cascade diagram, find the pinch point on the cascade diagram, determine your QH, your QC from the cascade diagram. Take these three pieces of information, QH, QC, and pinch point, and plot your streams, identify the matching above and below the pinch, and verify that these numbers are valid when connecting these when developing your heat exchange network. Okay. And if something's not clear, just let me know or come to office hours. But this is really the approach. The common tripping point, if you practice a problem by yourself and these numbers don't add up for some reason, the way to troubleshoot it, first of all, check that your matching is correct. Check that you copied these numbers properly, you calculated your delta H's properly. Double check this. If this looks fine, go back to your cascade diagram, check you did your additions correctly for the Q's, and check you were able to identify the correct pinch point. If this is correct, go back to your interval table and make sure you copied the numbers properly from the interval table to the cascade diagram. If this is fine, take a look at your interval table and is all the information correct? Were you able to identify summation CP hot minus CP cold correctly? And Just this is really the critical step where if all of the previous troubleshooting step fine, then this is or is going to be, unless you copy the number incorrectly from the prompt, then just revise all your calculations accordingly. But yeah, when troubleshooting, do it systematically, backwards, step by step. Don't take multiple steps backwards when troubleshooting, because at least from last year's batch, they tended to do that, and it makes it harder to catch the error, right? Because once you jump a bunch of steps, now you have to iterate back and forth until you find your error, and it's going to take you a lot longer. Anyways, so this is problem number 1. Let's move on to problem number 2. So I'm going to clear all my drawings here, and let's share the problem set. Okay. So problem number 2, again, very similar idea. I have 4 streams, 2 hot, 2 cold. I need to match. I need to just build the interval table, cascade diagram, all that stuff. Okay, so let's, the only thing to note here is that the CP values are, 0.15, 0.225. They can, you might end up with a bunch of decimals, which might make your calculation a bit messy. But anyways, it's not a big deal. Let's solve this problem. So I have problem 2. And again, first step, I'm gonna rewrite or write the information I'm given. So I have stream number, T source, T target, CP. I have H1 goes from 300 to 80, CP of 1.15. H2 goes from 200 to 40, CP of 0.225. C1 goes from 40 to 180, CP of 0.2. And C2 goes from 140 to 280, and CP of 0.3, right? And the other piece of information I'm given is delta T minimum is 20 degrees Celsius, right? Okay, so let's solve this problem. So step 1, we said subtract delta T minimum from your hot streams. So 20, this is 280, 60, 180, 20, right? I have 2 hot streams, subtracted 20 from all these temperatures. So now let's move on to step 2. Step 2, let's use the same language we used last time. Arrange temperatures from highest to lowest. And identify your intervals. So let's do this. So my temperatures will be, what's my highest temperature here? 280. Second highest temperature is 180. Third highest is 140, right? 280, 180, 140, and I have 60, 40, 20, right? 60, 40, 20. And really, how complex a problem is depends on how many intervals you have, at least at the first stage. And just be careful at this point. Anyways, so I'm going to do this graphically. So I'm just going to draw horizontal lines next to each temperature. And here, these are my intervals. So this is interval 1. Right. This is interval 2, 3, 4, 5. So I have 5 intervals in this problem: 280, 180, 140, 60, 40, 20. Okay, now let's plot them. So I have H1 goes from 280 to 60. H2 goes from 180 to 20. C1 goes from 40 to 180, 180 all the way to 40. And C2 goes from 140 to 280. Is that correct? 140 to 280 is C2. It's fine. 140 to 280. So once I get to this stage, step number 3, build the interval table. And again, your interval table will have 5 elements. As we said, it will be interval number, first one. Second thing will be the initial temperature of the interval, the delta T of the interval, summation of Cp hot minus summation of Cp cooled of the interval, and finally delta H of each interval. And let's populate this table by looking at this diagram here. So let's have a look at interval number 1. The initial temperature is 280. The delta T of this interval is 100. Summation of Cp hot minus summation of Cp cooled, I have H1 minus C2. So it's 0.15 minus 0.3. So it's minus 0.15. And delta H for this interval is just this multiplied by this. Or your summation, your summed out heat capacity flow rate multiplied by delta T. Minus 0.15 multiplied by 100 is minus 50. Okay, let's have a look at interval 2. Initial temperature is 180. Delta T is 40. Summation of Cp hot minus summation of Cp cold. All of the streams are present, so I'm going to add the 2 hot streams and subtract the 2 cold streams. So it'll be 0.15 plus 0.225 minus 0.2 minus 0.3. 0.15 plus 0.225 minus 0.2 minus 0.3. This is minus 0.125 multiplied by 40. I'm going to get minus 5 in this stream. Let's have a look at interval number 3, which is this guy. Initial temperature is 140. Delta T is 140 from minus 60. This is 80, right? And summation of Cp hot minus summation of Cp cold. I have H1 and H2 and C1. So I have H1 plus H2 minus C1. So I'm going to add 0.15 plus 0.225 minus 0.2. And this is 0.175. And delta H in the stream is 14. Okay, let's have a look at interval number 4. Initial temperature is 60. Delta T is 20. Summation of Cp hot minus summation of Cp cold. I only have 1 hot stream and 1 cold stream, so it will be H2 minus C1, H2, 0.225 minus C1, which is 0.2. And this will be 0.025 multiplied by 20. This will be 0.5. Okay. And finally, interval 5, initial temperature here is 40. My delta T is 20, right? 40 minus 20 is 20. Summation of Cp hot minus Cp cold. I only have 1 stream here, which is H2. H2 has a Cp of 0.225. Right, so if I multiply 0.225 by 20, this will be 4.5. Okay, so now I have my interval table. Next step will be to translate this onto a cascade diagram. So let me save this screen right here. Let's get rid of this stuff at the top. And I'm going to erase my interval table as well. Okay, and now I'm going to build the cascade diagram. And the first step of building the cascade diagram will be just draw a bunch of boxes equivalent to a number of intervals. So I have 5 intervals. I will draw 5 boxes. So I have 1, 2, 3, 4, 5, and just connect them with some arrows. This will be your cascade diagram or your cascade tree. Sorry. And then I'm going to translate or, move the information from here onto the cascade diagram. So let's do this. So first interval here, Ti, or initial temperature of this interval is 280. The delta H of this interval is minus 15. The initial temperature of the second interval is 180. The delta H in this is minus 5. The initial temperature of the third interval is 140. The delta H here is 14. The initial temperature of so this is the fourth interval, 460. And the delta H in this case was 0.5. Let's rewrite this properly. This was 40. And the final interval, the initial temperature was 40, and the delta H in this case was 4.5. And this is step 4. Let's just write it here. Step 4 will be diagram, step 4, and then step 5 we said is to add the Q for each interval, right? So I'm going to determine the Q for each interval. And again, start off by QH is equal to 0 at the top. Q1 in this case, 0 minus 15 minus 15. Q2 minus 15 minus 5 is minus 20. Q3 minus 20 plus 14, 6. Q4, 6 plus 0.5 is 6.5. And Q5 or QC at the bottom here, 6.5 plus 4.5 is 11, right? Is 11. Okay, so now I determined all of my Qs. So next step will be find pinch point, which is at the most negative Q, right? So let's have a look here. I guess we can call it 6. Let's have a look here. Where is my pinch point? Where is my most negative Q? 0 minus 15 minus 26, 6.5, 11. This is my pinch point, right? Let's use another color. This is my pinch point right here. So this is pinch point. My temperature, cool temperature at the pinch is this temperature is 140. And my hot temperature at the pinch is 140 plus delta T minimum. Delta T minimum for this problem was 20. So this will be 160. Okay, find the pinch point, and then step 7, I'm gonna add enough heat. Add Q, or add QH at the top, so that Q at pinch is equal to 0, right? So I'm gonna add enough heat at the top so that this Q here is 0. So in this case, I need to add 20. So QH plus 20 is 0 plus 20. Minus 15 plus 20 is 5. Minus 20 plus 20 is 0. 6 plus 20 is 26. 6.5 plus 20, 26.5. And then finally, QC plus 20 or 11 plus 20 is 31. So once I get to this point, we said, I think we called it step 7.1 last time. right? Identify your metrics for building the network, right? I need these three numbers. QH 20 megawatts, QC 31 megawatts, and T pinch is 140 degrees Celsius for the cold and 160 degrees Celsius for the hot. Okay, and these are the parameters I really need to start, or to start designing my heat exchange network. So you got to this point, we built the cascade diagram, we have all our numbers. Now let's start building our heat exchange network for this problem. So let me save this problem. Let me write these numbers here somewhere so I can remember them. So we have QH is 20 megawatts, QC is 31 megawatts, and the pinch point 140, 160. Okay. Let me save the screen, let's clear everything. Now let's start building our heat exchange network. Okay, so I'm still problem 2. Build the heat exchange network, and you may write these parameters. So we set QH was 20 megawatts, QC 31 megawatts, and my cold pinch was 140 degrees Celsius. My hot pinch was 160 degrees Celsius. Okay, so let's start, let's start doing this network. So again, first step, I'm just going to draw my streams. So in order to do this, I have H1 here. It goes from, let's move this up a bit. So I have H1 here. It goes from 300 to 80. And again, I'm using the original temperatures in this case. 300 all the way to 80. I have H2. It goes from 200 to 40. I have C1 goes from 40 to 180. And I have C2 goes from 140 all the way to 280. So I'm just drawing my streams. Once I get to this point, I'm gonna just draw two dividing lines in the middle to divide this problem into above the pinch and below the pinch, right? And for the hot streams, I'm gonna write my hot pinch temperature, which is 160 and 160. And for my cold streams, I'm gonna write my cold pinch temperature. Okay, and once we get to this point, we're gonna clean this diagram. So let's have a look here, 30 to 160, 160 to 80, decreasing, and then decreasing again. That's fine. For H2, I go from 200 to 160, 160 to 40. So it's sorry, for H2, I go from 200 to 160, 160 to 40. So it's decreasing, decreasing again. That's fine. For C1, I go from 40 to 140 and then 140 to 180, increasing and then increasing again. That is fine as well. And then for C2, I'm going from 140 to 140 and then 140 to 280. So there is no delta T here. There's no heat transfer because there's no temperature driving force. So I'm going to clean this line and just draw it above the pinch because C2 will only exist above the pinch. So I'm going to redraw C2 only above the pinch. So this will be C2, and the starting point of C2 is the same as my pinch temperature, so 140 to 280, so that's fine. So once I get to this point, I'm ready to start matching these streams. However, it's always good to just put in some metrics before you start your matching. Okay, let me clean out this. This is C1 goes from 40. Okay, so the metrics I put is delta H and CP. Delta H because I need to know how much heat is available in the stream, and CP because the matching rules depend on CP, right, which is the heat capacity flow rate. So I'm gonna calculate these parameters here for these streams. So I'll just start off writing the CP. So it's 0.15, 0.225 for C1, 0.2, 0.3. There is no C2 below the pinch. And here we said it's 0.15, 0.225, 0.2, and 0.3. Now let's calculate the values for delta H. So here, 300 minus 160, this is the delta T above the pinch, multiplied by CP, which is 0.15. So I'm gonna get 21 for H1 here. For H2, it's 200 minus 160, multiplied by 0.225. This is 9. In this case, for C1, 180 minus 140 multiplied by 0.2. This is 8. And for C2, 280 minus 140 multiplied 280 minus 140. That's 140, right? Multiplied by 0.3. This is 42. Okay. Now let's go below the pinch here. So I have 160 to 80. That's what 80, right? 160 minus 80 is 80. Multiplied by 0.15. This is 12. Delta H available in H1 below the pinch. For H2, 160 minus 40. So for H2, 160 minus 40 multiplied by 0.225. 160 minus 40. Yeah, I'm not sure. My camera keeps on disconnecting, but that's fine. So I have 160 minus 40 for H2 below the pinch. So delta T for H2 is 120 multiplied by 0.225. It's 27 right here. For C1, 140 minus 40 is 100 multiplied by 0.2 is 20. So I have my delta H's above and below the pinch. Let's just verify these numbers again. So I have 160 minus 80. 160 minus 80. This is 80 multiplied by 0.15. This is 12. Then I have 160 minus 40 multiplied by 0.225. This is 27. And then I have 140 minus 40, which is 100, multiplied by 0.2. This is 20. Okay, so we have a calculation error here. Let's go through this problem and then we'll try to troubleshoot this error towards the end. Yeah, we have a calculation error here. 18. Let's have a look. Let's just go to the previous screens and try to troubleshoot it. Let's see where we went wrong. Okay. Okay, this was the last whiteboard we had. Let's just double check. Or actually, let's move on to the whiteboard before it. How do I do? Let's open the whiteboard where we're doing the.
Dr. Basha,
Yes.
I think Q3 is supposed to be, it should still be negative, right?
Q3. You mean the cascade diagram?
Yeah.
Q3 is. Oh yeah, so minus 20 plus 14 is minus 6, right? Okay, good. Yeah. So here's the error. Thank you. Yeah, so we did an addition error here. So when I was adding my Q's actually, so I have 0, minus 15, minus 15, minus 15, minus plus 5, sorry, minus 15 minus 5 is minus 20, minus 20 minus 14 is minus 6, that's right. Minus 6 plus 0.5 is minus 5.5, and then minus 5.5 plus 4.5 is minus 1, right? So you see here should be minus 1. And then if I add 20, it should be 19, right? Okay, so let's just note this error. I'll have to, yeah, just note this error down. So our QC is actually 1 and not 31, right? Thank you very much, that's good. Okay, let's go back to the whiteboard. Let me just fix this QC here. Sorry, yeah, it's 19 because it was minus 1 plus 20, and I'm just going to, someone's watching this. Someone's trying to do this at home. Okay, anyways, so our QC now is 19. So now I think we can start matching without any issues. And the way to catch this error really before doing any matching on this diagram is you could simply really just add all the delta H's here and all the delta H's here and see if it makes sense. So here I have 21 plus 9 minus 8 minus 42, right? I have the two hot streams have 21 plus 9 minus 8 minus 42. So if I do a quick calculation here, 21 plus 9 minus 8 minus 42. This is equal to minus 20, right? And this number should always match this number. On this side, if I add my two hot streams, 12 plus 27 minus my cold stream, which is 20, this was equal to 19. And this number now matches this number. Previously was 31 when I was like looking here. It doesn't look like 31, so there's something wrong. And you can always stop here and go back instead of wasting time and matching and wasting a lot of time doing this. Anyway, so we know that if we match correctly, we should be able to get to these numbers. So let's write the rules of the matching. So above the pinch, we said CP hot is less than or equal to CP cooled, and we have no cooling, right? Should never cool the hot streams above the pinch, and below the pinch, CP hot has to be greater than CP cold, and there is no heating. I should never heat the cold streams below the pinch. Okay, so now let's start matching. Let's have a look at H1, 0.15. I want to match it to C1, H1 and C1. 0.15 is less than 0.2. So I can make this connection. So I'm going to connect these two guys. H1 has 21 megawatts. C1 only needs 8. So I'm going to transfer 8 only. And C1 is done above the pinch. H1 still has some heat left. How much heat does it have? 21 minus 8. And this will be 13. Okay, let's have a look at, or let's try to get rid of all this heat in H1. So H1, let's try H1 to C2, 0.15 versus 0.3. CP hot is less than CP cold, 0.15 is less than 0.3, so I can make this match as well. So I'm gonna connect H1 again to C2, and this one, H1 has 13, C2 needs 42. So I'm just gonna transfer 13 megawatts from H1 to C2, and now H1 is done. C2, I only transferred 32 megawatts, so it still has some energy left. So 42 minus 13 is 29. So C2 still has 29 megawatts of cooling, which it needs. Okay, let's have a look at H2 now. CP is 0.225. The only cool stream is C2. 0.225 is less than 0.3, so I can make this connection. So I'm going to connect these guys here from H2 to C2. This stream has 9. This stream needs 29, so I'm going to transfer 9 megawatts. So now H2 is done, and C2, I give it 9 minus 29, 20. So still has 20 megawatts, which I need to supply somehow. So I'm going to add a QH equal to 20 megawatts, and this number matches this number basically, right? So algebraically, the system is valid. So now let's look below the pinch. Again, the rule CP hot has to be greater than CP cooled. So let me look at H1 to C1, CP hot 0.15 versus 0.2. I can't make this connection, it's not gonna work. So let's forget about H1 for now. Let's move to H2. H2 to C1, 0.225 to 0.2. This connection works. 0.225 is greater than 0.2. So I can connect these two streams with a heat exchanger. And H2 has 27. C1 only needs 20. So I'm going to transfer 20 megawatts from C1 to H2. Good. So now C1 is done. H2 still needs 7 megawatts. There are no more cold streams. So I'm going to use my cooling utility to just cool these streams. So I'm going to have my first QC here, 12 megawatts, and then my second cooler here, QC, 7 megawatts, and then 12 plus 7 is equal to 19, which means the system is valid. So this becomes our heat exchange network for this problem. And this is the optimum design where I use the minimum possible cooling utilities and I maximize use of available heat in my process. Okay, good. Let's save this. Save the screen, and now let's clear it, and let's move on to problem 3. Okay. So problem 3 here, I have given the following streams and delta T minimum is 10 degrees Celsius. Again, build the interval table, cascade diagram, determine the pinch point, minimum heating utility, cooling utility, heat exchange network. So same type of problem. Let's go to the whiteboard and just go through the steps of solving this problem again. So now we're doing problem number 3. And I'm just writing what's given. We have delta T minimum is 10 degrees Celsius, and our streams in this case are, so let's write the information we have. So I have stream number, source temperature, target temperature, and my heat capacity flow rate right here. So my streams are 1, or let's call them H1, H2, H3, I have C1, C2, C3. And let's write our temperatures. I'll just list them as is: 170, 278, 354, 30, 130, 200, my cold 88, 90, 100, 135, 205, 298, and my heat capacities are 23, 2, 5, 23, 2, 5, 9, 20. Okay, so I have all my temperatures here. So step 1, I'm going to subtract delta T minimum from my hot stream. So in this case, it will be 10. I'm going to subtract it from my hot streams. 170 minus 10, 160, 88 minus 10, 78, 278 minus 10, 268, 80, 340, 490. Okay, so I subtracted my temperatures. Next step, I'm going to arrange my temperatures from highest to lowest. Okay, let's be careful here. We have a bunch of temperatures. So let's try to do this properly. So I have 344 is my highest temperature. So my first will be 344. This is done. Let's put a dot next to it or something. The next highest temperature is 298. So this is done. Third one is 268. Right. Then I have 205. I have 200. 200. Then there is 160 right here. Then there is 160 is done. There's 135 actually. Good. Then I have 130. Okay. 55, 130. And then I have these three guys, right? 90, 80, 78. Okay, so let's maybe give ourselves some space. Let's write it here. So we said 344, 298, 268, 205, 200, 160, 135, 130, 90, 80, 78, and 30. So you have a lot of intervals in this problem. That is fine. Just do the steps and we'll be able to find the solution. Let's just double check we have the right temperatures. 344 at the top, 298, 268, 205, 200, 160, 135, 130, then 90, 80, 78, and then finally 30. Okay, so good. We have our intervals here. Now let's let's plot our streams on this table or on this diagram here for the interval. Okay. So I have H1 goes from 160 to 78. H1 goes from 160 all the way to 78. H2 goes from 268 to 80. So H2 goes from 268 all the way to 80. I have H3 going from 344 to 90. 344 all the way to 90. I have C1 going from 30 to 135. So C1 is from 135 all the way to 30. C2 goes from 130 to 205. 205 to 130. And C3 from 298 to 200. 298 to 200. Let's just double check this. So I have H1 from 160 to 78, H2 from 268 to 80, H3 from 344 to 90, C1 from 135 to 30, C2 from 130 to 205, and C3 from 298 to 200. Okay, so we have our table here. Let's just count how many intervals we have. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 intervals. So let's start building the interval table. Let me save the screen and let's erase these guys. Let's build the interval table here. And I'm just going to write the CP values next to these streams just so that avoid looking back and forth. So this is 23, 2, 5, 9, 20. Let's build the interval table. So our interval table will have 5 elements, as we said. So I have my interval number, my initial temperature, my delta T, summation of CP hot minus summation of CP cold, and delta H. So let's start populating this table. Let me write this properly here. This is interval number. Okay. Anyways, so interval number 1, the initial temperature is 344. The delta T is 344 minus 298 is 46. Summation of CP hot minus CP cold. I only have one hot stream, which is H3, and the CP is 5, so this value is 5. Delta H now will be 5 multiplied by 46, and this is 230 kilowatts, right? Interval 2, initial temperature is 298, so I'm looking here now. Delta T is 298 minus 268. This is 30. Summation of CP hot minus CP cold. I have H3 minus C3, 5 minus 18. This is minus 13, and my delta H will be minus 13 multiplied by 30, this is minus 390. Okay, interval 3, initial temperature is 268. The delta T is 268 minus 205. This is 63. Right, 268 minus 205 is 63. Summation of Cp hot minus Cp cold, I have H2 plus H3 minus C3. So I have 2 plus 5 minus 18. So this is 2 plus 5 minus 18. This is minus 11. And delta H will be 63. Multiplied by minus 11 is minus 693. Interval 4, initial temperature is 200. No. Interval 4, initial temperature is 205. My delta T is 205 to 200 is 5. Summation of Cp hot minus Cp cold is H2 plus H3 minus C2 minus C3. So it's 2 plus 5 minus 20 minus 18. This is minus 31. Delta H minus 31 by 5 is minus 155. Okay, interval 5, which is this guy, 200. Initial temperature, delta T is 40. I have H2 plus H3 minus C2. 2 plus 5 minus 20. This is minus 13. And delta H is minus 13 multiplied by 40 minus 520. Good. Interval 6. Initial temperature is 160. Delta T is 160 minus 135 is 25. Summation of Cp hot minus Cp cold, H1 plus H2 plus H3 minus C2. So it's 23 plus 2 plus 5 minus 20, 23 plus 2 plus 5 minus 20, that is 10. And delta H is 10 multiplied by 25, which is 250. Okay, interval 7. Initial temperature is 135. Delta T is 5. 135 minus 30. Summation of Cp hot minus Cp equal H1 plus H2 plus H3 minus C1 minus C2. 23 plus 2 plus 5 minus 9 minus 20. 3 plus 2 plus 5 minus 9 minus 20. This is 4. Nope. 23 plus 2 plus 5 minus 9 minus 20 should be 1, correct? And delta H is 1 multiplied by 5 is 5. Okay, interval 8, initial temperature is 130. Delta T is 130 minus 90 is 40. Summation of Cp hot minus Cp cold is H1 plus H2 plus H3 minus C1, so it's 23 plus 2 plus 5 minus 9. 23 plus 2 plus 5 minus 9. This is 21. And delta H is 21 multiplied by 40. This is 840. Interval 9 now. Initial temperature is 90, right? Delta T is 10. 90 minus 80 is 10. Summation of Cp hot minus Cp cold is H1 plus H2 minus C1. So it's 23 plus 2 minus 9. Minus 9, this is 16. And delta H is 16 multiplied by 10 is 160. Interval 10, initial temperature is 80. Delta T is 2. Summation of Cp hot minus Cp cold, I have H1 minus C1. 23 minus 9. This is 14. 14 by 2 is 28. And then finally, interval 11, initial temperature 78, delta T 78 minus 30. This is 48. Summation of Cp hot minus Cp cold, I only have 1, which is 9. It's going to be minus 9. And the amount of heat available in this interval, 48 multiplied by -9 is -432. So this is our interval table, and now we're ready to translate this into a cascade diagram. Before doing this, let me just verify the calculations. 5 by 46 is 230, 30 by 13, 390, right? Okay, so our multiplication is fine. Let's translate this onto a cascade diagram and determine our metrics. So I'm gonna erase this figure right here. Okay. And again, the first step in doing a cascade diagram is drawing number of boxes equal to the number of intervals you have. So let's do this. And again, I have 11 intervals, so you just have to be careful in the space of it. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then I'm gonna connect these with arrows. Okay, and now I'm just going to translate the information from my cascade diagram from my interval table onto the cascade diagram. So let's start. I'm at the very top. My initial temperature is 344, and my delta H is 230. On this stream, in the second interval, sorry, my initial temperature here is 298, and my delta H is minus 390. On the third interval, my initial temperature is 268. My delta H is minus 693. My fourth interval, my initial temperature is 205. Oops. So I'm here, and my delta H is minus 155. My initial temperature here is 200. My delta H is minus 520. Here it's 160, and my delta H is 250. $135, delta H is 5. 130, delta H is 840. 90, delta H is 160. 80, delta H is 28. 78, delta H minus 432. Okay, so we moved all the information here. Now let's calculate our Q's at every interval. So starting from the very top, we have our QH is equal to 0. Our Q1 here is 0, plus 230 is 230. Q2 is 230, minus 390 is minus 160. Q3 minus 160 minus 693 minus 853. Q4 minus 853 minus 155 minus 1008. Q5 minus 1008 minus 520 is minus 1528. Q6 minus 1528 plus 250 minus 1278. Q7 minus 1278 plus 5 minus 1273. Q8 minus 1273 plus 840 minus 433. Q9 minus 433 plus 160 minus 273. Q10 minus 273 plus 28 minus 245, and then finally Q11 or QC at the bottom here, minus 245 minus 432 minus 677. So this is our Qs. Let's just verify the numbers. 230 minus 390 minus 693 minus 155 minus 520 plus 250. Okay, so they look fine. So now let's identify the most negative point along this cascade diagram. And this will be right here, right? This is my most negative point, and this is where my pinch point is. So now I'm gonna just identify my pinch point. So this is my pinch point really, and my temperature at the pinch. Actually, let's get right here, and T is 160 degrees Celsius for the cold, and the T hot pinch is 160 plus 10, right? So it's be 170. So this is my pinch point, and now let's add enough heat so that the temperature at the pinch point is 0. So I'm gonna add plus 1528. And I'm just gonna move this along the diagram here. So plus 1528, 230 plus 1528 is 1758. Is 1368. Is 675. $520, and this, 0. This is 250. This is 255. This is 1095. $12.55 right here. $12.83. $8.51. Okay, so once I get to this point, I have my okay, so I have my metrics I need for my heat integration. So in this case, so I got to this point, I have my QH, is 1528 kilowatts. QC is 851 kilowatts. My pinch point is 160 for the cold, 170 for the hot. And these are the numbers I can, or my integration targets, which I'm going to use to build my network. So my QH is 1528, my QC is 851, and my pinch point is 60. Okay, now let's start building our heat exchanger network and see how we're going to do this. Again, this complexity of this problem really just lies in having a bunch of intervals and a bunch of streams. It just increases your error in making, increases your chance in making calculation errors, right? So it just tests how organized you are, how focused you can stay throughout all of this. Okay, let's clear all this junk now. Let's build our integration or our network. So I have QH, let's just write our targets here. QH is 1528. QC was 851. My cold pinch was 160. And my hot bench was 170. Okay, let's draw our streams and let's start building this network. So I have H1, first of all. It goes from 170 to 88, 170 to 88. I have H2. It goes from 278 to 290. 278 to 90, sorry. 278 all the way to 90. I have H3. This guy goes from 354 to 100. To 100. And then I have C1. Goes from 30 all the way to 135. I have C2 from 130 to 205. Okay. And then I have C3, which goes from 200 all the way to 298. Let's verify. So it's 170, 278, 354, 30, 130, 200, and then it's 88, 90, 100, 135, 205, 290. Good. So we have our streams here. So I'm gonna just draw my two lines down the middle here to divide this problem into above and below the pinch. And we'll start taking a closer look at this system. Okay, so above the pinch, or for the hot pinch is 170. So I'm gonna write my hot pinch temperature 170, 170. For the cold streams, the pinch is 160. Okay, now let's clean up this diagram. So for H1 goes from 170 to 170, 170, 88. There is no delta T here, so there can't be any heat transfer. So I'm gonna clean this line. So H1 only exists below the pinch. So I'm gonna draw H1 below the pinch here. From 170, right? That's the right temperature as well. To 88. Let's have a look at H2. 278 to 170, 170 to 90, decreasing, that's fine. H3, 354 to 170, 170 to 100. Decreasing, decreasing, that's fine. C1 30 to 160, 160 to 135, so it's increasing and then dropping. This doesn't make sense, so so C1 only exists below the pinch, right? It goes from 30 to 135 below the pinch and it stops there. So for C1, it exists completely below the pinch. It goes from 30 all the way to 135. C2, 130 to 160, 160 to 205, increasing, increasing, that's fine. And C3, 200 to 160, 160 to 180, so it's decreasing and then increasing. Doesn't make sense. So C3 exists completely above the pinch from 200 to 298. So C3 in this case will exist completely above the pinch here from 200 all the way to 290. Okay, so now our diagram is ready to start matching. And before doing this, or before doing our matching, let's write the metrics we usually write for these problems. So again, I'm gonna list my CP and my delta H for each stream above and below the pinch, just to give myself some information. Let's write it this way. Delta H here and CP. Now let's just write the values for the CP which are given. So I have 23, 2, 5, 9, 20. C3 does not exist here. And again, we said it's 23 and it doesn't exist. 2, 5, 9, C1 doesn't exist. Above the pinch 20, 18. And let's determine the amount of heat available. So above the pinch here, H2 278 to 170, 278 minus 170 is 108 multiplied by 2, this is 216. H3 354 minus 170 multiplied by 5, this is 920. For C1, or sorry, C2, 5 minus 160, 45 multiplied by 20, this is 900. And for C3, 298 minus 200 multiplied by 18, this is 298 minus 200 multiplied by 18, this is 1764. Okay, so now let's have a look at on this side. And again, you can always double check your numbers here by just adding, 216 plus 9. So if I do a quick check before doing anything, so if I just add all my hot delta H's minus my cool delta H's, 216 plus 920 minus 900 minus 1764, this will be 216 plus 920 is equal to minus 1528. And this matches this. So, if we match properly, we should be able to get the right system. Let's have a look here, 170 minus 88. 170 minus 88, 82 multiplied by 23, this is 1886. $170 minus 90, this is 80 multiplied by 2. This is 160, 170 minus 100, 70 multiplied by 5, this is 350, 135 minus 30, 105 multiplied by 9, this is 945, and 160 minus 130, 30 multiplied by 20, this is 600. Now let's verify on this side, 1886 plus 160 plus 350 minus 945 minus 600, this is equal to 851. So we're this system, this side is valid. If you want to check 1886 plus 160. So adding all the hot, subtracting all the cold is the same as that number we have at the top. So if we do the matching properly, should be able to get the numbers we want, the optimum numbers. Let's put it this way. Okay, so let's write the rules before we do any matches. So above the pinch, we said CP hot has to be less than or equal to CP cooled. And there is absolutely no cooling. And below the pinch, we said CP hot has to be greater or equal to CP cooled. And there is absolutely no heating. Okay, let's match these streams. So I have H2. Let's start with H2, sorry. CP is 2. CP hot has to be less than CP cold. Let's C2. Let's match it to C2, which has a CP of 20. 2 is less than 20, so I can make this connection. So let's connect these guys, connecting H2 to C2. How much heat am I transferring? H2 has 216, C2 needs 900. So let's just transfer all the heat from H2. So this is done. And here I have some energy still needed. 900 minus 216. I have 684, which I need to provide. Okay, let's have a look at H3 in this case, has a CP of 5. Let's try to match it to C2. 5 is less than 20. This stream has 920. This stream needs 684. So I can make this connection. So let's connect these guys. So I'm going to connect this. And you can, if you see that there are other options and you want to pursue the other options, you can do that. You're still going to get the same number of exchangers and coolers, right? So the number will be the same. So if you want to connect 920 to here, that's fine. And, you're going to have a cooler here and a cooler here versus 920 to here and then to here, and then only having a cooler here. It's the same type of thing. Anyways, so H3 has 920, C2 needs 684. So I'm going to provide 684 from this stream to this stream. And this way, C2 is done. And H3 still has some energy, which is 920 minus 684, which is 236. There's no cooling above the pinch, so I need to get rid of all the heat in these hot streams. So let's have a look. H3 to C3, 5 versus 18. I can make this connection. So I'm going to connect a third heat exchanger here from H3 all the way to C3. And this has 236. This needs 1764. So I'm going to transfer the 236 from this guy to this guy, and then H3 is done. And I still have some cooling requirement here, which is 1764 minus 236 is equal to 1528. So I'm going to add a cooler with 1528. I think it's kilowatts for this problem, right? Kilowatts. And then there's overall cooling is equal to this number, which means the system is valid, or this system meets the minimum energy targets. And again, if you want, you could, instead of making this connection, instead of making these two heat exchangers, you can just connect one heat exchanger from H3 to C3, and then you're going to have two heaters actually. Sorry, this has to be QH. There's no cooling above the pinch. And it's a cold stream, so I'm heating it. So this has to be QH. Just be careful with these notations here. Anyways, this is a QH. QH, and then you're going to have two heaters. One on C2, one on C3, but your overall number of connections will be the same, right? You're going to have 4 connections here. Anyway, so above the pinch, we're done. Let's have a look below the pinch now. The rule of this game is CP hot has to be greater than CP cool. Let's try to make these connections. H1 has a CP of 23, and C1 has a CP of 9. So I can make this connection. So let's connect H1 to C1. C1 needs 945, H1 has 1886. So I'm going to transfer 945 from H1 to C1. Then now C1 is done. And H1, I still have some energy left, which is equivalent to 1886 minus 945, which is 941. Okay, let's have a look. H1 to C2, 23 versus 20. 23 is larger than 20, so I can make this connection. So let's just make this connection here as well. From H1 to C2, C2 needs 600. H1 has 941, so I'm going to transfer 600 from H1 to C2. So now C2 is done, and H1 I still have some energy left here, equivalent to 941 minus 600, which is 341. I don't have any more cold streams to transfer the energy from the hot streams, so I'm going to add 3 coolers. QC 341 here. For H2, I'm going to cool it as well, equivalent to 160. And for H3, I'm going to add a cooler equivalent to 350. And if I just sum all my QCs, I should get 851. 341 plus 160 plus 350. And this is equal to 851. And this means our system is valid, or, you know, this meets the minimum energy requirements for this process. Okay. So this is problem 3. I'm going to stop here. Problem 4 and 5. So problem 5 is a very long problem. You just have 4 hot streams and 4 cold streams. You're going to have a bunch of intervals, and it's similar to problem number 2. So you can exercise it, you can practice it if you want. It's not necessary, but if you want to test your concentration, you can practice problem number 5. Problem number 4 again is, it has 3 hot streams, 3 cold streams. So, and the numbers are all strange, you know, 189 to 86, all the CPs are a bunch of decimals. And problem number 4 is really a problem designed to be solved by Excel, where you minimize all these arithmetic errors. But you can practice it as well if you wanted to try and test your concentration. But generally, these are the steps. I'm going to stop here, just solving 1, 2, 3. Please make sure you know how to solve these problems. Your exam will only have these types of problems. So be prepared. If you are not prepared, come to office hours this Thursday. I'll have office hours all day. I might also have office hours on Friday. Make an appointment if you want to, but it's very important that you're comfortable going through these steps. Okay, and practice 1 or 2 or 3 problems before the test as well, just to get a feel for it. Okay, I'm going to stop here today. Thank you very much, guys, if you're still listening. And yeah, if you have any questions, let me know.
Thank you. Have a good day, Dr. Basha.
Take care. Thank you.